Today I want to talk about methods and approximations in AC analysis. I think I've said before that there's a lot of things I like about Malvino. However, one of the things that he does is he starts using approximations rather quickly and before the students really know what's going on. He's been doing it a long time. He knows which things can be thrown away pretty quickly, but you guys sometimes don't. So I'm just going to point out some differences or some areas where he's approximating, and you need to be aware of that. Okay, so number one, if you recall, this is our schematic from our voltage divider bias circuit. I did this example in another video. Actually, looking at this one, I recognized a couple of things. There's a few typos in here. I got Zn equals RB1 parallel to RB2 times beta plus 1 multiplied by R prime E plus RE, which should be 333, and I put 330 here, so 333.5. You can keep that in mind if you're watching the other video that's a typo. And then I also made some kind of mistake down here. I must have been thinking about a different problem. I wrote down 223. This should be 333. I think I have another video where RE is 220, and that must have been still on my mind. Okay, so there we are. Let's talk about some of the approximations on here and places where you don't have to be as exact as the exact method. And when I say the exact method, even that's not really super exact. When you do multi-sim, it takes a lot more things into consideration than the exact method we do by hand. Hand calculations are to get you an approximate value to see if it's biased and to kind of have an idea what the gain is. If you want to go further than that, then things like multi-sim and simulation tools will take in many more things into consideration and get you a more accurate result. Okay, so approximation number one. Beta plus 1 versus beta. Does this really make a difference? This idea of, I always insist on saying beta plus 1. And the reality is, if beta is 100, the difference between 101 versus 100 is really an insignificant value. I do an example here. I say Zn, and I calculate it out using 101, and I came out with 11.8K. And then I calculated it out using beta of 100, and I came out with 11.8K. Maybe 50 ohms difference, like fourth digit down significance. So I'd say that's not really something that you need to be aware of. The only thing that using beta plus 1 does is it kind of emphasizes that you understand the concept, that the base current adds in with the collector current, and the emitter current is the biggest. This beta plus 1 versus beta thing tells me that you know that this is the biggest current and it's the sum of these two. So usually when I'm asking for that, it's so that I know you're not just memorizing formulas and getting them wrong. Okay, so there's the first approximation. This is a reasonable approximation that you can use beta instead of beta plus 1. And that's how it applies to Zn. If we're looking at gain, does it make a big difference on gain? Well, if it's, so gain, I think this formula was, when we're figuring out AV, that's IC over IE times RC over R prime E plus RE. So that's going back to this sheet. That's basically this thing down here. If I skip the beta over beta plus 1, how much impact does it have on the final answer? So right here. And the answer is that basically it's a 1% error. If this is 0.999 something, 0.998, and this is 1. So I'd say for so far as gain is concerned, it's a reasonable approximation. We really don't even know the value of beta. The value of beta could vary by 10%. So using this 100 over 101 thing on a number that could be 90 to 91 really doesn't make any difference. So this is a reasonable approximation. However, there are always conditions where it may matter. What if beta's low? What if beta's 10? What do you got a big power transistor that's pushing lots of current and doesn't have a huge gain? Well, all of a sudden, if you use 10 versus 11, then Zn would be 75K parallel to 20K parallel to 10 times that or 11 times that. That's like 33K or 36K. That's a 10% error. And that's probably someplace where it's not a reasonable approximation, that you need to probably use beta plus 1. So don't be assuming that just because it works in most situations that it works in all of them. Okay? So that's the first thing we talked about, beta versus beta plus 1. The next thing that we may want to look at is this R prime E here. It came out to 3.48 ohms in series with 330. Does that really matter? Well, let's see here. If we look on Zn, if I take this as basically 101 times 333 versus 101 times 330, I'd say that that's not numerically significant, and that would be a reasonable approximation would be to do it with beta of 100. So that's totally reasonable. And for gain, when we're calculating gain with R prime E, so gain, let's see, where did R prime E come in? Basically, it came in at the bottom here. So it was RC over the sum of them. What if it's just RC over RE? Well, that makes it 100 over 101 times 1,000 over 330. So this is with no R prime E versus 1,000 over 333. R prime E equals 3.5. Again, that's probably about a 1% error. The value of R prime E versus the rest of it, it's about 1% of the total impedance on the emitter. So R prime E is about 1% of this impedance. So I think that's a reasonable approximation that you can throw that away. For a voltage divider bias, for this circuit, that's reasonable. However, some of the voltage divider biases, they have a capacitor in there to ground the emitter, common emitter circuit. Well, if that's the case, then the emitter is grounded. And the emitter is basically grounded here with a capacitor. Let's take a look. So, or even in a base bias circuit, if this is grounded, now AV would be minus RC. It would be minus RC over R prime E. And R prime E all of a sudden is really important. Like, R prime E is everything in this. R prime E is everything in this example, and you cannot ignore it. And beta plus 1, if the gain is low, then it may still have an impact. So, yes, you can drop these things, but you need to do it with knowledge and not just go ahead and forget about them. Okay, so there's another section here. This topic for today was, what was the topic? Methods and approximations. So far I've talked about methods, or I've talked about approximations. Now I'm going to talk about methods. So the text has a little bit of it's different in section 8-9. It's different, but not different. And I'm going to show you what section 8-9 is. So section 8-9 is about voltage gain and with a CE amplifier. And so it kind of goes in here and it says, here's a voltage divider bias with this thing grounded. And it shows you the AC equivalent circuit with the pi model and with the T model. And then let's go to, then he kind of starts talking about, he starts using RC parallel to RL and AV. All of a sudden he's got the load in the calculation. And he's basically saying that the load is in the calculation here. And I've never put the load in the calculation. I've always insisted that you do the AV, solve AV for the no load. And he's also got a couple of terms that he's introducing here, RC and RE. So I just want to talk about what those are. So he's got R prime E, and he's got RE. So let me just show what that is. Okay, so here's the AC equivalent circuit. Here's the AC equivalent circuit that I've drawn. And he's introducing a new terms, RC and RE. And these are AC terms, they're impedances, they're in lowercase, so they're impedances. Basically what RC is if I stand here and I look out the collector, the transistor, what is the impedance looking out the collector? So what is attached to the collector of the transistor? So that would be RC. And sometimes, depending on what you're doing, sometimes we do it with load attached, RC parallel to RL, and sometimes we may do it with just RC. So you may, sometimes they specify what it is. RE on the other hand is you're at the emitter and you're looking out the emitter, what is attached to the emitter. And basically you just look at the resistances there and reduce them down to an impedance. And it's what's attached to the emitter. So RC is the impedance looking out the collector. RE is the impedance looking out the emitter. R prime E, that's inside the transistor. That's the impedance of the diode itself between the base and the emitter. This is all lowercase because it's AC impedances. Okay, so now he's going back to the gain here. Let's see if I can find this section here. And I think it's right here. He says, actually it's right here. He's saying that RC is RC parallel to RL, and then AV is RC over R prime E for that circuit. Let's take a look at that circuit. So 3,600 ohms on top, 1K here. He says that the gain, so he takes the 3.6K, puts it in parallel with the 10K, comes out with an RC of 2.65K. That is the impedance that is connected to the collector. And then he takes that value, 2.65K, and divides it by 22.7 R prime E, and he comes up with a gain of 117. This is the gain with the load attached. Let me show you what's happening here. So normally I would say when I figure out the gain for this circuit, I would figure out the no load gain. So I'd say it's minus beta over beta plus 1, negative because it's out of phase. So beta over beta plus 1 times RC over R prime E. So this is no load. I've taken out the load to figure out gain. So it ends up being 3,600. Let me go back there. So here I figure out the no load gain. I go minus B over beta plus 1 times RC over R prime E, which is 3,600 over 22.7. I get a no load gain of minus 158.6. That's the gain of the dependent source, which is inside the amplifier. If I now multiply this out, if I want to figure out what's appearing across the load, what I would do is I would multiply this 158 times 10K over 13K. I would factor in the voltage divider, and when I do that, I get minus 158.6 times 10K over 13.6K, comes out to minus 116.6, which is 117, which is exactly the same number he got. Okay, so he is calculating the final voltage that appears across the 10K. This is fine if all you got is a single stage and you just need to know what the gain of the thing all hooked up is. However, that's not really the way things work a lot of times. Sometimes you're given a couple of different amplifiers. You're given a two-stage amplifier, and the boss says, well, if we get this RF amplifier from this company and they got one that has these characteristics, what happens if we take that and we hook that up to this amplifier that we got down in the shop there? And basically you know what the characteristics of the amplifiers are, and you can say, oh, well, if I put 1 volt here, I can, I got a voltage divider, I know what's going into the second amp, and then it kicks it up, I can figure out what the net gain is from end to end. Okay? And then the boss says, well, this isn't going to work. 500 ohms and 8 ohms, that's not going to work. Can we improve that? And you come along and you say, well, I got this other one. Let's use that one. And he goes, hey, yeah, okay, that looks better. But, can we get a little bit more gain out of this first one? And then you say, okay, yeah, I can do that. I can maybe get, I got one that's got 20 and 100 ohm output. A little bit more power, a little bit more current gain. How does that look? That looks great, the boss says. What Malvino is doing is he's looking at this as a single stage problem. And if it's a single stage problem, he's throwing the load inside. Problem with that is, what the boss says, okay, I want to stick on a 4 ohm load. How do you take the 8 ohms out of here? You don't know what Z out is. You've lost the value of Z out. So if I change this from 8 ohms, it was 8, and now the boss says we need to drive 4 ohms. Is that going to work? Well, Z out in this one is a big question mark. You no longer know what it is, so you can't be swapping loads easily. You'd have to go out and figure out what the Z out of the amp is. However, if you're looking at it this way, and the boss says, well, what happens if there's 4 ohms stuck on it? Okay, that's what happens. And if the boss says, well, what happens if there's 2 ohms? Car stereo speakers come in 8, 4, or 2. Say, okay, that's what happens. So this is the reason I'm trying to get you guys to do the no load gain, the AV no load, or the open circuit voltage gain. And then we can start connecting functional blocks together and see how they work together.